How did Schrodinger derive his equation? He tried to express electron as waves where the phase is given by the action function that satisfied that equation. We do not know yet the value of the constant, but we'll get to that later. A compact way to write that equation would be in this form. Secondly, Schrodinger was interested in electron waves that had time-independent amplitude, meaning stationary solutions. So he said that if an electron had constant energy, the wave amplitude shouldn't fluctuate with time. It should be independent on time. So he was looking for constant energy stationary solutions. So he wanted in space to describe electron wave amplitude fluctuations that didn't change with time. He wanted stable solutions as electron around the proton. He wanted some kind of wave configuration that was through space, that was somehow stable, for stable electron, not electron transitioning. And so he assumed that it was time independent. And he preferred to write it that way. So we know that introducing the complex, the imaginary number into an exponential we find that it's a compact way to write sine and cosine by considering function that have values in C. So C is simply the real number plus a imaginary component. So this function has value in the complex numbers. And so he was interested by that equation. So he used the normal wave equation, which was because a solution of that equation would be a sine phi, where a is constant. So there could be solutions where a is not constant, but he was interested in solutions where a was constant, and you would find that the function obeying that equation would be such that the wavefronts would evolve that way. Suppose you took an initial wavefront. What you would do is for time equals epsilon, you would take each point on that wavefront and trace a normal to that wavefront at each point. And along that normal, you would add a distance of v epsilon. The v could be a variable function of space or even time, but let's say it's not dependent on time. So if v would vary from point to point, the distance that you would trace on each normal would be different. Sometimes it's short, sometimes it's long, depending on v epsilon. And then you would take the points on each of the normal and interpolate a new surface that passes through each of these points along each possible normal of the initial surface. And that new wavefront would still equal to c, but at a later time. So the fact that this v would be a speed of evolution of wavefronts of constant phase along normals. So, but for the case where A is not constant, you would find that the equation obeying that differential equation would have wavefronts that do not propagate exactly at V, but close to it. So using the same logic, Schrodinger asked, what is the speed of propagation along normals of wavefronts S equals C, where C is fixed, but time increases. I defined the speed earlier here as saying you start with that initial wavefront, you traced normals on each possible points, and for a small variation of time, you added v epsilon to along each normal, and then you traced a new wavefront that passes through all those points that are v epsilon meters away from the initial wavefront. So this is how we define v, a speed of propagation along wavefronts. So how was he able to find the speed of propagation along normals of the action function of wavefront of electrons? What he would do is he would take a point on an initial wavefront and he would say that as time evolves, the point on that initial wavefront will evolve also, so that the wavefront will maintain its phase equals to c, to a constant. And also, second assumption, we want dA over dt, dB over dt, and dC over dt to be proportional to the normal of S uh, along the wavefront. So it would be proportional to, say, the gradient which is normal to the wavefront. So differentiating both sides with respect to time. Since this is a constant equal to 0, and by the rule of partial derivatives, the chain rule of partial derivatives, we can say that these three are symbolic to say that we want to take the partial at AT, BT, CT. This is what we mean by the partial derivatives. And here, these are total derivatives of the moving point along normals of the wavefront that maintains its phase, as we saw earlier. So all of that is equal to 0, and we know that ds over dt is equal minus E, where we fixed it for all electron paths through the wavefront. So rewriting that, since dt over dt is equal to 1, and this we can rewrite also. So it's minus E plus ds over dx. The inner product with this is the equation from which we're gonna extract the speed of propagation along the normals. So we already assumed that the evolution of that point, the point will be always proportional to the normal of the wavefronts as the wavefront evolves. So as the wavefront evolves, the point on it will move along the normals. So the velocity is actually defined as we want to find the velocity, and the velocity is defined as so this is how we define the velocity of how the points of the normal evolve into new points of the new wavefront for a fixed phase as time increases. So v will depend on position, but not on time. This is given by the grad of s, and this is the length of the vector n. So it's simply is the length. So the length is given by this. You just want to normalize the vector n. So that new vector, if you take the inner product with itself, is going to be equal to 1. So it's unit length, unit normal. Can extract the values of these quantities from the Hamilton-Jacobi equation. So let's rewrite that equation. It's minus E plus this is the velocity of the point on the moving wavefront that we said that moves normal to that wavefront. And we want to find the value of V. So by product, we can see that this here so we see that V times the absolute value of the normal is equal to E. So V is equal to E over the absolute value of the normal. The absolute value of the normal is given by this. We know from the Hamilton-Jacobi equation so we would like to isolate that part here. So rearranging, this is minus E So if we return to the equation for the velocity at the velocity of how the wavefront propagates along its normal, we can rewrite it as so this is the right equation.